Okay, good morning. Welcome to our lecture number 13. Today we will be looking at a new topic. This topic is called first order circuits. In first order circuits, we'll be dealing with transient responses, as we will see later on, for circuits that are made of source free. What does source free mean? Means that there are no sources, no independent sources to drive those circuits. We have two types. So the first type is called RC circuit, which basically means that we have a circuit that has no source. The capacitor has an initial voltage stored in it, has energy stored in it, and now this energy is going to be dissipated into the resistor. The second type is source-free RL circuit. And here I need to mention that when I say first order circuits and I say RC circuit, this means I only have capacitor and resistors. I don't have inductors. And when I see RL circuit, this means I only have inductor and resistors. And that's why we call this response as natural response, because basically the response is going to be based on the energy that is already stored in those two components. No sources of energy, they're the only source of energy, and basically they're going to dissipate their energy into the resistors that this capacitor or this inductor is seeing. And this resistor is the R Thevenin resistor. So when you later on calculate the resistance, you need to find the resistance that this capacitor or this inductor is seeing, which is basically all the equivalent resistance that is connected in parallel with this capacitor or this inductor. So as I said, natural response depends here on initial conditions that are already do exist in the capacitor or the inductor. Then we will introduce the unit step function that we will basically defines the operation of a switch. So the operation of a switch basically means a unit step function. When you have this switch open and then goes to close status, you have unit step function from off to on. So this basically resemble a unit step function. Then we will look at the step response. The step response here of an RC circuit. And again, the whole uh, definition of first order circuits is having a capacitor and resistors, or an inductor and resistors. I don't have a mix of inductor and capacitor in the same circuit. This is not first order circuits. So here in the step response, we will be looking at the response that going to exist when I have an energy source in my circuit. So in this case, it's not going to be a natural response or pure natural response. It's going to be a mix. So here in the step response, we're going to have, as we'll see later on, a mix of responses. But in a step response, we do have independent sources. We're going to see what those independent sources are going to do to the transient response of my circuit. Step response of an RL circuit. Basically, we're going to look at the transient response for a circuit that has an inductor and resistors with the existence of independent sources. So two main types: an RC or RL circuit that has energy stored already in it, and now there are no other sources, and now this energy is being dissipated in the resistors. This is the natural response. And then a step response basically due to the existence of an energy sources, and we're going to see how is this circuit going to behave. So let's first start with the first order circuit for definition here. As I said, the name first order circuit is because of first order differential equations. Remember the relationship between the voltage and the current for the capacitor or the inductor, the first order differential equation. So here we have, as I said, two types. We have RC circuit, which is basically a capacitor and resistors, and we have an RL circuit, which is basically an inductor and resistors, right? And we said that we have two types of excitations, the natural response and the step response. The natural response is due to the energy stored in this energy storing component, and the step response is due to the existence of an independent source, which are energy sources here that are basically going to result into either charging or discharging the capacitor based on the difference between the voltage for the capacitor or the current for the inductor. We're going to come to this in details. So the first one, source-free RC circuit. I have a circuit made of a capacitor, and I have a resistor also in this circuit. So if I am to find the relationship between the voltage here for the capacitor, I know that the voltage across those two components are the same. If I take the KCL at this node, I know that IC plus IR equals to 0. Now, let's assume that this capacitor has an initial value of V naught, so we can later on see the voltage relationship that we can derive for this capacitor. So this capacitor has an initial voltage here of V naught, and now it's being connected to this resistor. So what's going to happen? The energy stored in this capacitor is going to be dissipated into the resistor. Now, if I look at this KCL, the equation that I got here, remember that the current for the capacitor is C dV over dt, right? Following the passive convention. And for the resistor, IR is indeed equals to the voltage, which is the voltage of the capacitor divided by R. So this is IC, this is IR. If you add them and rearrange by dividing by C both sides, you're going to get this expression. Now, this is a first order differential equation, and the differential part came here from the relationship between the voltage and the current for the capacitor. So the solution for this expression is from the exponential type. So what is the general solution to such first order differential equations? The solution is from the exponential type, which is Vt equals to A times e to the power st. This is the general solution for such first order differential equations. Now I need to calculate for A and for S. So how do I do this? If you take this function and substitute it into the expression that we found, dv over dt plus v over rc equals to 0. If you substitute this in here and rearrange, you will find that S would be minus 1 over RC. And then if you substitute here VT, then After you find S equals to minus 1 over RC, the function becomes Vt equals to A e to the power minus T over RC. Now, if you substitute the initial condition, so here V at T equals 0, and this equals to V naught, remember, equals to A E 0. In this case, you find that A equals to V naught. So the function that we have calculated for a source-free RC circuit is the following. Vt equals to V naught E to the power minus T over RC. So this is the function that describes the behavior of a voltage across a capacitor that is connected in parallel, that has an initial condition, which basically means that has an initial energy stored into it. And now this energy is being dissipated into the resistor. It's an exponential function. So keep this in mind. First order differential equation has an exponential solution. And this exponential solution for the RC circuit is the following. Vt equals to V naught e to the power minus T over RC. Now, what is this RC? We're going to talk about that in a couple of slides, but this response is called the natural response. A capacitor that has an initial energy stored in it, and then you connected this capacitor through resistive circuit. What's going to happen? This energy is going to be dissipated into this resistor, or into this equivalent resistance. As we will see later on, we will be looking at R Thevenin, the equivalent Thevenin resistance. So we call this the natural response. As you can see, the capacitor has a voltage V naught right at the initial when t equals to 0, and then the response is going to be exponential, right? So we call this response that starts from an initial voltage, initial energy stored into it, and then connected through a resistive path. We call it natural response. Is going to end up being fully discharged. So this response is an exponential response, and we call it the natural response. No external excitement and natural response. Now, we said that we're going to talk about this RC, and this RC, we call it the time constant. And what does it mean? The value of the capacitance times the value of the equivalent resistance that this energy is seeing define what's called tau, the time constant, which is basically how long does it take for the voltage to decrease from this initial voltage to 36.8% of this initial voltage. So in other words, if this is my V naught, right? Find the 36.8% of this V naught here on my scale. Then find this time. This is going to be my tau. This tau that is R, again, as I said, this should be the R Thevenin. If it's a circuit that has several resistors into it, RC. This tau is the time it takes for the voltage across the capacitor to decrease from its initial value to 36.8% of this initial value, right? So this is the point, 36.8%, which is 0.368 V naught, and this is the corresponding tau, and this tau equals to R Thevenin C. So that's how we got this 36.8% of the initial value. It is, if you take this function that we have talked about, which is V t equals to V naught E minus T over tau, as you can see here. If you calculate the value of the voltage when T equals to tau, substitute T with tau, you're going to end up with this reference value, which is e to the power minus 1. So this defines the 36.8%. So at T equals to tau, I will be reaching a 36.8% of my initial voltage. This is for the, again, RC circuits that are source free. Any questions so far? So the value of the time constant change based, as we have seen, on RC. So if you have a small resistance, you have a small tau. If you have a small, as you can see, proportional, the relationship is proportional to R and C. Now, we can approximate the time it takes for this capacitor to be to become completely discharged. We found that 5 tau is enough. Why? Because at 5 tau, you have reached almost less than 1%. You do the calculations by substituting t with 5 tau, and you will see that the the value that you're going to reach is less than 1%. So 5 tau for us is enough to reach the steady state, right? The transient, the exponential function is considered to be over 5 tau and above. So if you look at those three signals, both of them are starting from the same initial voltage, 1. However, tau here is 0.5, tau here is 1 second, tau here is 2 seconds. Notice that at 5 tau, so the 5 tau for this is 2.5, which is here. This is 5 tau for this function. Right? For the second function that has tau of 1, 5 tau is here. So this one is, so for every tau, 5 tau is enough to reach the steady state response. Yes, yes, you can use 5 tau as the time, an approximation to less than 1% error, which is enough for us. So at 5, after 5 tau, you'll be either reaching, if the capacitor is being charged, you will be reaching the full charge, which is, we're going to call it the steady state, or if it's a source of free circuit, you would be reaching the full discharge. So 5 tau is enough for us. Yeah, it will. So this is, as I said, the voltage response for RC source of free circuit, starting from V naught and being dissipated. So don't forget that the tau is R Thevenin C, whatever the value of your capacitor, and then you should be looking for the R Thevenin if the circuit is made of more than one resistor. In our example here, we have only one resistor connected across. So here it is tau is RC, right? And in later examples, as we will see later on, the circuit may be made of several resistors. So in this case, we should be looking at R Thevenin. So this is the voltage. If you want to find the current into this resistor, then definitely those two components that we have seen, which is the capacitor and the resistor, they share the same voltage, right? If I'm calling this one VCT, and this is the resistor. So in this case, if this is VCT or VT, here, this is VT and this is VT, then definitely the current into the resistor would be this VT divided by R, right? Which is V naught over R e to the power minus T over tau. What about the power dissipation? The power dissipation is V times I. V times I, which is V naught e minus T over tau times V naught over R e minus T over tau. And that's V naught squared divided by R e to the power minus 2T over tau. What is the energy? If you do the integration on the power from 0 to T, you're going to get the energy as a function of time as the following. What does this mean? Recall the response for this source free, right? If this is V naught, this means the energy at T equals 0 is what? Is 0, right? Why? Because when T equals 0, one minus E0, this is going to be 0. Then if you calculate at T equals to 5 tau, what are you going to get? Half C V naught squared. If you substitute 5 tau here, you're going to get almost 0. So this one is going to be half C V naught squared. In this case, the whole energy will be dissipated, right? Now, if you want a more accurate representation, instead of 5 tau, put infinity. You're going to get 0, right? Any questions so far? So, in summary, we have seen that a source-free RC circuit has an exponential response. It has an initial voltage because there were initial energy stored into it, and now the circuit is made of this capacitor that's acting as the only source, and now it is dissipating its energy into the resistors that are connected to it. If it's a single resistor, then it is R. If it's a circuit, then you have to find the R Thevenin that this capacitor is seeing. We will see this in an example. The response is an exponential response, right? And the time it takes to reach 36.8% of the initial value of the voltage is called tau. Okay? Then you can also calculate the current, calculate the power, and calculate the energy based on the circuit that you have. Now let's look at this example. Here things would become clearer about what I have just introduced. In this circuit, we have an initial voltage stored in the capacitor that is 15 volt. I don't have any other source in the circuit, so my energy in this capacitor is the only source of energy. So in this case, and as I have seen, that the relationship is an exponential relationship. So Vt, which I'm calling here Vct, is indeed V naught E minus T over tau, right? Now, in this expression, in order to find the voltage Vc, I only need to find those two constants, V naught, which I have, in the expression, for the expression itself, I have V naught. Sometimes I don't have V naught, I need to find how much is this V naught. But here I have V naught, and the second parameter is tau. So I know V naught, I need to find tau. How do I find tau? As you can see here, the circuit that this capacitor is hooked up to has several resistors. It's not one distinguished resistor that the energy is going to be dissipated through. So what do I do in this case? Can somebody tell me what do I do? I know C. R net is 20. Mm, not really. So I need to find, as I said, R Thevenin C. So I will redraw my circuit here and I will remove 5 in parallel. That's correct. So 5 in parallel with 20. So in this case, I will redraw my circuit and remove the capacitor and find the R Thevenin between those two electrodes. So here, or nodes, I will remove this capacitor here. And now my resistive circuit that I would like to find the R Thevenin across is the following. I have here 12, I have 8, I have 5. So my R Thevenin is indeed 5 and 20 in parallel. So this is going to be 5 times 20 divided by 5 plus 20, and R Thevenin would be 4 ohm. So I found R Thevenin that I will be using for my tau. So my tau now becomes R Thevenin 4 times the capacitance 0.1, then tau is 0.4 second. So I found now VCT. So VCT is indeed 15 e to the power minus t over 0.4, and this is volts. So this is how we find the voltage expression across a capacitor that is in a source of free circuit. So I'm done with VC. What about VX? Can you tell me what is the relationship between VC and VX? Any idea what is the relationship between VC and VX? They are not the same. No, they are not the same. Look at the voltage. Look at the voltage across the the capacitor. isn't this voltage across the capacitor the same as the voltage across the 8 and the 12 together that are in series? So what does this mean? What does this mean? The voltage across the capacitor is indeed across the two resistors that are in series. How can I calculate Vx? Vx as a voltage is a portion of voltage division. Voltage division, that is correct. So Vxt, keep in mind that Vx is also a function of time, right? Because once Vc changes exponentially, everything is changing as well exponentially. So Vxt is indeed Vct times 12 over 12 plus 8, right? So this is the voltage Vx, which is 12 divided by 20, that equals to 0.6. So I have here Vxt is zero point 0.6 of this 15, which is 9 e to the power minus t over zero point 0.4 volts. So this is Vxt. Now what about Ix? Can somebody tell me how can I find Ix? And again, it is a function of time. Because the voltage is a function of time, now everything is becoming a function of time, right? And everything now is related to this exponential response. So what is Ixt? Ixt is the current that goes into this branch, right? So this is Ix. Vx over what R? Give me the value of R. 12. That is correct. So Ixt is Vx divided by 12. So this is going to be 9 divided by 12 e to the power minus t over zero point 0.4. And the unit here is ampere, right? The unit is ampere. So keep in mind that Ohm's law are also applied in our circuits here. Example number 2. Okay, so now remember when I told you that the initial condition for the capacitor was given in our example number 1 and not necessarily given, you have to find it. Here is what's going to happen. Now here the switch in the circuit has been closed for a long time, and keep in mind when you have a circuit that has a switch, as we have said before, you have to redraw the circuit. You will be having two different circuits, right? So the question here is saying the following: the switch in the circuit has been closed for a long time and it's opened at t equals 0. We need to find Vt, which is the voltage across the capacitor. So as I said, here we have a circuit that has a capacitor, has a source. So the switch was closed for a long time. I will redraw the circuit for the switch that was closed for a long time. And in this case, keep in mind what's going to happen to the capacitor if you have a switch that is closed for a long time. When the switch is closed for a long time, what's going to happen to the capacitor? we have seen this in our previous lectures. When I have, remember the DC conditions, the circuit is being closed, which means it is under DC conditions. What's going to happen to the capacitor? What's going to happen here to this capacitor? Exactly. The capacitor is treated as an open circuit, right? But this does not mean that the voltage is zero, right? The capacitor is being treated as an open circuit. What does this mean? The voltage I will be calculating now across this capacitor is going to be used as what? VC, and I will call this one 0 minus. Why did I call it 0 minus? Why did I call it this one VC 0 minus? Because the question is telling me the following. He's saying that at t equals 0, the switch is going to be open. So this is the last moment before the switch was open. And it's coming from this circuit that is at steady state. Why? Because the switch has been closed for a long time. So in other words, the capacitor has already reached its maximum charge. It has across it a voltage that I will be considering as my initial voltage for the next stage when my switch is open. Remember, we have said before that the voltage across the capacitor is continuous and does not change instantaneously. So if I am to look here at the switching, if this is the time of 0, the time of the switching, and this is the voltage across the capacitor would have a voltage that is acting like this because it's steady state. It's been in this state for a long time, right? And then this is the moment of the 0 minus. Now the capacitor, once the switching happens, the value after the switching is not going to change. The value right here is going to stay the same. And this is at 0 plus. Only that moment. Only that moment when I do the switching, the value right before the switching should be the same as the value right after the switching, and then we'll start changing exponentially. But only this moment right after the switching, which is right after the 0, and that's why we call it 0 plus. So in this case, we will say that the voltage for the capacitor at 0 minus equals to the voltage of the capacitor at 0 plus, and now this one is going to be my initial condition. So this is the way to find my initial condition. Why? Because here, this is the circuit before the switch was open. Now this is the circuit right? So from this circuit, when the switch was closed for a long time, I should be able to find the VC 0 minus because it belongs to the stage, the moment, the last moment before the switch was open, and it is the same as the moment after the switch was open, and it is my initial value. So how much is the VC 0 minus here? VC 0 minus here, the voltage here is the same as the voltage across the 9 ohm, right? Why? Because the current here is 0. Remember when we said that when we have a resistor that is an open circuit like this, the potential at this point becomes the same as the potential at this point. So in this case, VC0 minus, which is the voltage across the capacitor, becomes the same as the voltage across the 9 ohm. And in this case, this would be a voltage division, right? Because VC0 minus equals to 20 times 9 over 9 plus 3. And in this case, 9 times 20 equals to 15 volt. So VC0 minus, which is the VC0 plus, which is the V naught here, is 15 volts. So I can come here, 15 volts, right? Now, what's going to happen to this 15 volt once I open the switch? I'm sorry. No, because I am calculating the voltage across the 9 ohm. So VC0 minus, the same as the voltage across the 9, and this is coming from the 20 volt, right? So it's a voltage division. The 1 ohm is an open circuit, has no current going into the 1 ohm, right? So my VC0 minus is the same here as well. And it becomes a voltage division. 9 divided by 3 plus 9. 9 divided by 3 plus 9. I am calculating VC 0 minus from my first circuit, which is this one, when the switch was closed for a long time. The switch was closed for a long time, and that's why I drew this circuit. And then after that, when the switch was open, this is now my new circuit. Now the V node, which is the 15 volt, is in this circuit now. I found the initial from the first circuit. So the whole purpose of the first circuit is to find your initial, knowing that the VC0 minus equals to the VC0 plus. So this is your entrance from the first state to the next state. The entrance is this boundary condition, that VC0 minus equals to the VC0 plus. How can you find the VC0 plus? By finding this VC0 minus, because they're equal, right? So this is your entrance. So you're using the first circuit to help you find the initial for the next circuit. So now here in the next circuit, in this circuit, you have a capacitor that has an initial of 15 volt. Right away now you can say Vt equals to V naught e to the power minus t over tau. V naught, you already calculated V naught to be 15 volts, and tau to be RC, and here this R is 10, and this C is 20 milli, then tau is 200.2 second, right? And then Vt becomes 15 e to the power minus t over zero point 0.2 volts. Okay, is this clear? Okay, that's good. So those are the two examples for the source of free RC circuit. Now let's move to the source of free RL circuit. Here, the analogy is not that different, except we're dealing with currents. The uh, the quantity that is continuous in RL circuits is the current in the inductors. The current in the inductor does not change instantaneously. So, in this case, as we will see later on, we will use IL 0 minus equals to IL 0 plus, and this would be your initial current passing into the inductor. So, again, looking at source of free RL circuit, I have an inductor that is connected here with a resistor, as you can see. Applying a KVL is going to result into VL plus VR equals to 0. And then using the passive convention, this VL is LdI over dt, and that's where the first order differential equation came from, plus Ri equals to 0. Rearranging, dividing uh, by here by R, both sides, you're gonna get first order differential equation, exactly the same of what we have seen earlier. The solution after substitution of my general uh, solution for a first order differential equation, which is an exponential function, and solving for the two constants, you're gonna end up with this expression for source-free RL circuit. The same, I have initial current, and now this initial current is being decaying exponentially, right? With one difference here, that the tau for the RL circuit is not RL, it is L divided by R. This is the tau, and that's the tau, the time the current reaches 36.8% of the initial current. So the same, right? Tau is the time the response reaches 36.8% of the initial current. So the response is exponential. First order differential equation. Response is exponential. I have initial and I have the second constant, which is the tau. I find this tau from the inductance divided by the resistance. And if it's only one resistor, that is R. If you have a bunch of resistors in the circuit, then you have to find R Thevenin, exactly the same way we did for the capacitor. Now the function we need to understand is the unit step function, which basically represents the switch that we have seen. On, off, on, off. So this on may be something, and this off will be completely different thing, right? So we were going to look at this, but the unit step function is defined as the following: 0, and at t equals 0, I have a change. And that's why I called it on, off, or off, on. It depends. But here it goes from the step function is defined as 0 before the switching, and then at t equals 0, it jumps to 1. So this is the unit step, and it's defined by mathematically this way. The function is 0 before the action that's happening at t equals 0, and it is 1 right after. Or it could not it should not be 0 at t equals 0. The action may be shifted, as you can see here, at t nod. So in this case, at t nod, not necessarily 0, but at t nod, an action happened to my circuit, defined by this unit function. So this is just to link the switch mathematically to one of the functions that we have seen, which is the unit step function. But what we care about here is the interpretation of this unit step function in my circuit. So let's look at this voltage, source that is multiplied by a unit step function. Again, what does it mean? Before t equals 0, it is 0. So a voltage source that is 0 is basically represented by a piece of wire. That's why before the switch, the voltage was 0, and this meant that I don't have a voltage source, I only have a piece of wire. At t equals 0, the voltage source now is switched into the circuit. And this means that this switch, as you can see here, is going to move up such that I have a voltage. So this is the definition of, as I said, between the on-off thing. So for the voltage, an off voltage source means a piece of wire. But let's look at the off current source. An off current source means an open circuit. Look, when I multiply this current source by this unit step function, before it was 0. And what does 0 mean for a current source? An open circuit. So this is how the circuit looked like due to the switch, due to the unit step function. A current is 0 before t equals 0. It means it was an open circuit, this way. A current is on now at t equals 0. Means that this has moved to this second position. So this is just to show you what does a 0 source and an on source mean. A 0 source for the voltage means a piece of wire. So this is position 1, this is position 2. A 0 current source means an open circuit, right? So here is position 1. So the circuit is open, and then this is the position 2, when the current source gets switched into the circuit. So this is only to explain to you how's this on off thing means for different type of sources. But for me, the most important thing for me is you understand how does this switch operate. When the switch is at a position, and then how is the circuit going to behave? And then this switch has moved to a second position, how is the circuit is going to behave? And always keep in mind the definition of this switch has been at this position for a long time. Means that this is a steady state, which means capacitors is an open circuit, inductors are short circuit when the switch has been at this position for a long time, or the DC under DC conditions. Both are the same. When this switch has been there at this position for a long time, this means that this circuit is under DC conditions. Capacitors are treated as open circuit, inductors are treated as short circuit. For the capacitor, you need to calculate the voltage drop across it, because this one is your entrance to the next stage. Why? Because VC0 minus equals to VC0 plus, right? So it is your key towards solving the problem, and this is going to be your a value that will help you to find the initial condition. Same thing for the inductors, but it should be the current. The currents for the inductors are the ones that are continuous, the ones that do not change simultaneously. So the value of the current at 0 minus equals to the value of the current at 0 plus. Now let's look at the step response of an RC circuit. Here where we have a voltage source that's going to be introduced to my circuit. In this case, I have a voltage source here, resistor, and a capacitor with the existence of a switch. And at t equals 0, I close the switch, right? So the capacitor may have some initial value, or this initial value may be 0. In general, you can take that it has an initial voltage stored into it. So how do I solve and find the relationship for the voltage across this capacitor? Again, apply KVL. If you apply KVL, so let me here redraw. This is Vs. This is the current, IC. This is R. This is VC. So if you apply KVL here, you are going to get minus Vs plus VR plus VC equals to 0. So minus Vs plus VR plus VC equals to 0. And then this VR is RIC, and this IC is CdV over dt. If you substitute in this circuit, right, and divide by RC, the expression is going to look like this. So this is a first order differential equation. However, as you can see, does not equal to 0. So by integrating both sides and introducing the initial condition, what is important for me that you know that now the voltage is Vs at, of course, t greater than 0, Vs plus V naught between two parentheses minus Vs e to the power minus to the power t over tau. So this is now the voltage response for a circuit and step response. So this is different than the natural response that you have seen. If you recall, the natural response was Vc t equals to V naught e to the power minus t over tau. This is for a capacitor that is being discharging, right? It has a natural response. And this response was exponential. Now, a capacitor that is being charged, let's look at it as a capacitor that being charged. The response is not only a natural response, as we will see, it's a mix of responses. However, the interesting thing that the response is also exponential. So being discharged, it discharges exponential. Even if it's charging, it will charge exponential. Now, let's look at this response. As I said, let's assume that this capacitor had an initial voltage across it. And then all of a sudden, I connected it to a source. I switched it in here such that now this source is connected to my circuit. What's going to happen? The capacitor is going now to charge from V naught to a second voltage, that is here the maximum voltage is going to see when it's at steady state. However, the charging response is also exponential. So keep in mind that the voltage is here Vs plus V naught minus Vs e to the power minus t over tau. Okay, so here the response is a mix. We have what's called the natural response and a forced response. The natural response, now if you rearrange this one, Vs plus V naught e minus t over tau minus Vs e minus t over tau. Now if I put the one due to the natural minus t over tau plus, I take here Vs outside, 1 minus e minus t over tau. Notice that this step response is made of a natural response and what we call here a forced response. The forced response is due to the existence of a voltage source, of my energy source. So that's why a step response is a mix of responses, natural response and a forced response. Okay, so this is the natural response that we talked about, and this is the forced response by decomposing this stepped response into those two responses. But for me, at the end, what is important is to find those constants in order to find the expression for the voltage response and a step response for an RC circuit. So for me, at the end, what I need to do is to find the Vs, which is the value across the capacitor at the second steady state, plus the initial. So this is the same, Vs is the same. So I need to find the value of the capacitor at the steady state, but the next circuit, the second circuit, not the first one. I need to find the initial, and I need to find the tau. The tau is being calculated from the second circuit. Is this clear? So from the first circuit, I find the VC at 0 minus. That is the same as the VC at 0 plus. That I will use it in the next circuit. From the next circuit, I find the steady state across the capacitor, and I find the tau also for my capacitor. Okay, so here another perspective. We can say that we can decompose this stepped response step response into two responses. One of them is a transient, the one that is responsible for the transient, and the one that is responsible for the steady state. So I can call this one as the transient because this is the one that is multiplied by the exponential function, and I can call this one the steady state. At the end, I need to find V naught, I need to find Vs, I need to find tau for the RC circuit with a step response. Now, a step response of an RL circuit, again, the transient is this. If you look at the transient, and the steady state would be Vs over R. But for me, what is important is I find the response. It doesn't matter how you look at it. It doesn't matter natural, forced response, or steady state, a transient. At the end, the summation is going to give me this function. So what I need to find for the inductor is the the steady state current from the second circuit, the initial current, again this is the same, and the tau from the second circuit, right? From the initial, don't forget that in order to find the initial, we find it from the I0 minus, that is that equals to I0 plus, and this is going to be my initial current in the inductor. I will show it to you how we do it step by step. Don't worry about that. We will do an example, probably in next lecture. We will do examples where we solve them, show you how to solve them in what's called a step by step approach. 1, 2, 3, 4, 5, and then you can find the expression of the voltage for the capacitor or for the current for the inductor. It is very systematic, but the most important thing is to understand what do those uh, parameters or constants mean. The initial current, the steady state current, and the tau for the inductor, or the initial voltage, the steady state voltage from the second circuit, and the tau from the second circuit for the inductor. When I say second circuit, is after the switch, the second position after the switch is being moved. So the step response for the RL, exactly here we're looking at an initial from zero, a, a current that is initial zero. In this case, look at the current. How is the current behaving? Going from zero and then increasing till it reaches the steady state current from the second circuit. And of course, the voltage here is going to decrease exponentially if this current is increasing exponentially in the inductor. Okay, so here we're starting from an initial. My initial here is zero. It could be a circuit that does not have an initial of zero. If the initial was not zero, if there is an initial current, then it will be I naught like this, and then it will go exponentially to the next Call this one Bs over R, for example. Right? But in all cases, the response is exponential. So always keep in mind, if a capacitor is being discharged from initial voltage, it will discharge exponentially till it reaches zero. If a capacitor is being charged in a circuit that has no inductors, which means first order differential equations, this voltage is going to increase in the capacitor exponentially. So the discharge is exponential, the charge is exponential for the capacitor. Same thing for the inductor. A current will decay exponentially in an inductor in a source of free RL circuit, or the current is going to increase exponentially in a step response RL circuit. How, how how to calculate those values is based on the expression that we have introduced, either for the voltage for the capacitor even being charged or discharged, or the current in the inductor being charged or discharged. So you need always to keep in mind that for the source of free RC or RL circuits, what you need is the initial voltage for the capacitor for RC circuit, right? And the tau. For source of free RL circuit, what you need is the initial current for the inductor and then tau. For step response RC circuit, you need to find the initial and the steady state from the second circuit and the tau for the capacitor. For step response RL circuit, what you need to find is also the initial current, the steady state current from the second circuit, and the tau. As simple as this. We will be seeing more examples in the next lecture. We'll be solving more examples. Any question before we conclude this session?
Sir, I was just wondering, do you know when the solution set for problem set 7 will be posted?
If you want it today, I'll try to post it today.
Okay, thank you.
You're welcome. Any other questions? No other questions? Okay, then. Thank you so much, and we'll see you in next lecture. Have a good day.